Okay, in the last video, we took the Laplace transform of g delta t of t, which was trying to model our impulse forcing. I did insert a note in that video, but in case you missed it, at the very end I inadvertently dropped a factor of 2. There should be a 2 in the denominator of this fraction. Okay. Now, the Dirac delta function is defined as the limit as delta t goes to 0 of the function g delta t of t. And of course that leads to this nonsense. It shrinks the time interval to just a single moment in time, but it raises the magnitude of the force to an infinite value. So this was a perfectly legitimate real valued function whose Laplace transform we were able to calculate. This is not a real valued function. But we're going to take a look at what we think we ought to get if we take the Laplace transform of this. Now, if I tried to take the Laplace transform using this definition, that's pretty hopeless, because that's not a real value. I can't do an integral in which I'm integrating an infinite value. It's simply not defined. Okay. But I'm going to take advantage of the fact that this has a relationship to something whose Laplace transform I know. So I'm going to say this is the limit, this is the Laplace transform of the limit as delta t goes to 0 of g delta t of t. Okay. Now, without the limit, I know what I get. We worked that out in the last video. Okay. Here, I'm taking the limit first, and then taking the Laplace transform. Okay. So, that's taking the limit, and then taking an improper integral, which is itself a limit of an integral. Okay, and an integral is a limit of a sum. Okay. If I were allowed, and that's a huge if I were allowed to switch the order of these things, I can take the Laplace transform, I get this. This is an expression that has delta t's in it. I could take the limit of this as delta t goes to 0. That would be great. Now, in math, we know that sometimes the order in which we do things makes a difference. That's why we have this thing called order of operations that we try to respect. Okay? But we also know that sometimes we can interchange things, and we can do things in either order and we get the same result. So there are some rules about what conditions need to be satisfied in order for me to be able to interchange these processes of taking a limit and taking a Laplace transform. Unfortunately, those rules don't apply in this case, because those rules apply to real valued functions, and that's not a real valued function. Okay. So, can I switch these? There is no rule that tells me that I can. So, definition. Not a rule, it's a definition. I'm going to define, other people have defined the Laplace transform of the Dirac delta function to be the limit as delta t goes to 0 of the Laplace transform of g delta t of t. There's no rule that says that that's what this is. This is a definition, because there's no rule that tells me how to evaluate this, because it's not a real valued function. Okay? So we define what we mean by it. Now, can we do that? Sure. We can define anything we want to. The question isn't, can we define things this way? The question is it a good idea? Okay. And if it makes you feel a little bit nervous, good. Because in general, if you're like, oh, I don't know if I can do that, let me just define a world in which I can, sometimes that's just not particularly helpful. But what we're going to do, what we've done is we've defined this. We're going to evaluate what this is, because I can now take the limit of this Laplace transform. Okay? And then we're going to see if it's useful. So we're going to look at some differential equations where we've got a forced harmonic oscillator with impulse forcing, modeled by the Dirac delta function. We're going to use Laplace transforms to solve those. We're going to see what sorts of solutions we get, and we're going to say, does that seem reasonable given the situation that we were trying to model? Okay. If it seems reasonable, this was a good choice. And since it made its way into your textbook, it probably was a good choice. It was. I'll give it away. Okay. But when you're doing something like this, where it's like, oh, there's no rule that tells me whether I can do that, I'll just define a world in which I can, this was motivated by legitimate math. It's sort of an educated guess that it might be useful if we defined things this way, but when you make an educated guess that a definition might be useful, you kind of have to check that it actually is. And very important that we recognize that this is a definition, because there is no rule for functions that are not real valued functions like this. Okay, so let's see if we can actually evaluate this limit now. So we're saying the Laplace transform of the Dirac delta function is, again, by definition, the limit as delta t goes to 0 of the Laplace transform of g delta t, which is going to be the limit as delta t goes to 0 of this lovely formula that we found. E to the negative sa over s times e to the s delta t minus e to the negative s delta t all over 2 delta t. Now, notice this doesn't have any delta t's in it, so that's constant with respect to delta t, so I'm just going to factor that out. So I'm going to get e to the negative sa over s times the limit as delta t goes to 0 of e to the s delta t minus e to the negative s delta t all over 2 delta t. Now, you will be evaluating this limit in homework problem number 1. I'll just point out, delta t is your variable, it's going to 0. That makes the top and bottom of this fraction 0. It's a pretty straightforward application of L'Hopital's rule. It's going to get you the right answer. I'm going to actually evaluate the limit as well. I'm going to do it using a more geometric argument than just using L'Hopital's rule, okay? Because it really is a cool argument, and it uses some fundamental ideas in calculus. Okay, so here, delta t is our variable, so I'm going to view this as the delta t axis. And I'm going to look at the function y equals e to the s times delta t. Now, I've drawn this with s being positive. If s was negative, obviously it would be an exponential decay function rather than exponential growth. Okay. Now, what I want to do is take a look at this. I'm also going to draw this as if delta t is positive. So here, this point would be the point delta t e to the s delta t. Okay. Over here, I would have negative delta t, and this point would be the point negative delta t e to the negative s delta t. Okay. Now, if I connect those points with a secant line, the slope of that secant line is going to be e to the s delta t minus e to the negative s delta t, that's the rise, over the run. Delta t minus negative delta t is 2 delta t. This expression, whose limit we're taking, actually represents the slope of a secant line. Now, as delta t goes to 0, both of these points are going to move. Both of these points are getting closer and closer and closer to 0. But that means that we're really taking the limit of a secant line. It's a little different from the way we usually do it. Usually we have, when we take the limit of a secant line, we would have one endpoint fixed and move the other endpoint closer to that. Instead, we've got neither endpoint is fixed, but both are approaching the same value, which would be the value of 0 that we would have in the middle. But if I take the limit of the slope of the secant line, so So the limit as delta t goes to 0 of the slope of the secant line, I know that ought to be the slope of the tangent line at delta t equals 0. Because that's what we're approaching. Okay? These 2 points would both be approaching a single point in the middle where delta t was equal to 0. But if I view this as a function of delta t, then y prime, which is the formula for coming up with the slope of the tangent line, would simply be s copies of e to the s delta t. That's a quick application of chain rule. And y prime, evaluated when delta t is equal to 0, would simply be s times e to the 0, which would be s times 1, which would be s. So, this limit is s. You should still do homework problem number 1. Now, if you want to do it this way and rewrite this argument, you're welcome to. You can also do it by L'Hopital's rule. I kind of think both ways are nice, so take a look at this. If you want to rewrite it, you can, but try it with L'Hopital's rule too. Confirm that you do get the same thing. But now I've got, okay, e to the negative sa over s times s. That's just going to give me e to the negative sa. So, with this definition, the Laplace transform of the Dirac delta function is just e to the negative s times a. All right, excellent. Now, was this a good definition? We're going to have to solve some differential equations and see whether those solutions we get using this definition seem reasonable so that this turns it into a helpful tool for modeling impulse forcing.